Dear students, in this video, we are going to learn about Kohennon self-organizing maps. By the name itself, these are related to like calculating the distance map, how we have done in radial basis functions. And this was developed by T.O. Kohennon. Okay, these are used for unsupervised learning, where we have the visualizing for high dimensional data by projecting it lower dimensional data grid. Okay, so if you have the high dimensional data and if you want to project with the low dimensional projection onto a lower dimensions, we can use this algorithm. So the basic features of these algorithms are shown here. So the structure consists of two layers. One is output layer, another is input layer. Each neuron is represented as input feature and it consists of a map. So the output will be not in the form of the network, it will be arranged in a 2D grid. Okay, so it will have a weight vector on the same dimension of the input network. And what is the working principle? The primary goal of this SOM is to map similar input data to the similar output layer. So whatever the similar input will be there, it will be mapped nearby to the neurons in the output layer. So this process is called as a competitive learning. So if I have the distance between the input and output layer or input and output neurons are less, this will be mapped on the output neuron layer. So the distance between input and the output neuron is more, it cannot be mapped over here. So this is a basic concept on the working principle of this one. So we'll see the step-by-step process. In this first step, we will initialize. So we will initialize all the vectors in the form of 2D grid. So till now we have only one weight vector. So we'll have the 2D weight vectors. One is X value and one is Y value. And then training, we will select the input vector on the network and we will find the best matching unit. So we will find a neuron whose weight is closest to the input vector using the Euclidean distance. Okay. So for example, I'll calculate the distance between two input 2D grid values. So which one is having the less distance? This will be paired as the closest one for the next process. Okay, so this is a BMU, best matching unit. So accordingly, we'll follow the next part. After that, adjust the weight according to the BMU and neighbor neurons move closer to the input vector. So after that, what I'll do, I'll adjust this particular weight of the each matrix, that is 2D grid. And then if this particular adjustment is going, all the vectors are becoming closer to each other, there is no requirement of weight adjustment. So the formula for the weight adjustment equal to W of t plus 1 equal to W of t plus alpha t dot h of b comma W comma t dot x minus W of t. So W of t is the closer weight vector at a time. Learning rate, it is a neighborhood function, determines the BMU on its neighbors, and X is the input vector. So this will be repeated until unless the distance between both are reduced. So what are the key features? The basic key feature is topology preservation and dimensionality reduction. So it will not change the topology. So whatever the input vectors are there, the topology property will not be changed. And dimensionality, you can reduce the dimensionality of each and every vector which are working on that particular neuron. And where we are going to apply. So first one is data visualization. So in 2D grid, making patterns, clusters, data are more visible. Then we'll go for the clustering part and feature extraction. So in order to group all the input vectors, we can use the clustering. And since it is an unsupervised learning, it will be very much easy for doing without any input signals or target outputs. Next, feature extractions. So for pre-processing, this will be used very effectively for any type of machine learning task. So now we'll start with one example. So here, if I see here, now you are seeing that we'll have the distance points. These are the points. So this is the X value. So and weight also will have some points. So it is a 2x2 grid. So X1 equal to X equal to 0.1, 0.8, 0.5, 0.2, 0.8, 0.7, 0.2, 0.9. Similarly, these are the 2x2 weight values. 1 second. So these are the weight values. First, this is the data preparation. Next one, initializing the SOM. Third step training. Suppose if I select an input vector 0, 0.1, 0.8. Now I have to calculate the distance between 0.1, 0.8 with this particular vector. So like this, I'll calculate for all the values. Now, what is the BMU? What is the best matching for this? Okay, this distance vector, which one is minimum distance? You have 0.22. So the best match for this particular is 0.33, 0.7. Because if I take the distance, here it is 0.64, it is 0.72, 0.32. So this formula is nothing but your Euclidean distance formula. So like that, I'll calculate all the best match units for all the vectors. So after calculating the BMU, then we have to go for the updation of the weights. If no other match is found, you have to update the weights. Because if we won't update the weights, again, we won't get the new one. So here our learning rate is 0.5. I'll update the weight with this particular formula. So for the BMU best match 0.3, 0.7. So new weight will be, so what is the old one? 0.3, 0.7 plus what is the learning rate? Alpha plus alpha into x minus w old. What is x here? 0.1, 0.8 minus 0.3, 0.7. So I'll get the updated weight as 0.2, 0.75. So like this, we have to update the weight. Finally, next step is repeat this process over reducing the learning rate and neighborhood radius. Means all the neighborhood points will come closer, because if you want to do the cluster, we have to reduce the distance between the 2 points. So this can be done. So what is the result? We'll have end of the training, the SOM will have organized itself such that similar input vectors activate neighbor neurons on the map. So all these particular similar neurons will be at the single place. So after that, we have to visualize in a 2D graph, because it will give output as a 2D grid where you can visualize all the values. Finally, we can say that this is most powerful tool for data visualization in clustering. Okay, so only the thing is we have to calculate the BMU between the 2 points. Then if there is no more gap is there, we have to update the weight. Again, I have to change this particular value. So this is the process in SOM. So next topic is vector quantization. So what is meant by vector quantization? So it is a technique for which will divide large set of vectors into groups. Okay, if you have some 100 groups, 100 set of vectors, I'll club into some groups. Exactly, it is clustering. So this is used in mainly signal processing, and it is used in compression, pattern recognition, clustering, etc. So what is the basic concept? Here we have the code book. Okay, the basic concept consists of code book. So the central concept of VQ is code book, which will have the code vectors used to represent the data points. Second one is the encoding. Each data vector is assigned to the nearest code vector in the code book. So I'll take one vector, input vector, and I'll assign to the code vector in the code book. Then decoding. The decode vector represents the data vector during the reconstruction. Okay, this is encoding part and this is decoding part. So first we'll encode all the data with the code book, then decode with the data after the reconstruction. So what are the steps? So first we'll start with the initial code book. This can be done using random selection or any algorithm you can use. Second one, assignment. We have to find out the nearest neighbor for that. Assign each data vector to the closest code book. That is code vector based on the distance. You can use the vector, same Euclidean distance, and adjust the code vectors to better represent. Like if there is no basic or actual or exact match for that, we can update all the weights. So finally, this has to be done until your code vectors becomes very small. Now, we'll see with the example. So here we have same example here. This is a X simple 2D data set, and C is our code vectors. So here 0.1, 0.8, 0.2, all these are values. And the code vector is this one. I have to match with this particular 0.1, 0.8 is exactly match with which code vector I have to check. Now, at each data vector, I'll start with 0.1, 0.8 with 0.2, 0.8 and 0.7, 0.3. See, so which one is closer to? So when I calculate the Euclidean distance, I found that 0.8, 1, 0 point is closer to 0.2, 0.8. This is closer to 0.7, 0.3. And this is closer to 0.7, 0.3. And this is closer to 0.2, 0.8. Finally, the assignment is these two code books are near to this one, and these two vectors are near to this code vectors. Finally, I have to update the code vectors. So C1 equal to, I'm updating the code vector accordingly. So it is 0.1 plus 0.2 by 2, and I'll get the final value C1 and C2. C1 and C2. So after calculating these code vectors, I can go for the next iteration. So if there is no change in this particular code vector or these values, I can stop here. And this formula is used for centroids. So by calculating the centroids between these two, we can calculate these values. Okay, so this is a simple procedure. First, what we are doing, we are taking one initialization code book and data set, finding the nearest code vector, then assigning to the code book, then finally updating the code vector with the help of the centroids. Okay, the application of this one vector quantization is data compression, speech and image coding, pattern recognition. So this vector quantization will effectively used for data compression. It is used for encoding speech and images, pattern recognition for clustering and classification. What are the advantages and disadvantages? Efficiency, it is more efficient. Simplicity, the algorithm is very simple and easy to implement. But the disadvantage is the loss of information. So it is a lossy compression technique. So the information will be lost. There is a chance of information loss. And initialization sensitivity. The quality of codebook can be sensitive to initial code vectors. So the code vectors have to be identified properly without any errors in that particular code vectors. Finally, vector, it is a powerful tool for compression and clustering. This mainly works on code vectors, and updating the code work, it will ensure that it will give the good approximation of data distribution. So this is related to two topics. First one is SOM and second one is vector quantization.